Let me discuss a phenomenon known as the Hall effect. It is a magnetic phenomena and associated with charges flowing. It's one of those topics that comes up in AP Physics and in practical situations as well, in technology. The technology is, in a simplistic way, you can think of this as the foundation of a magnetic probe. What is the size of a magnetic field? So let's take a look at this. You notice I mention positive carriers, I also mention negative carriers. Kind of the idea of negatives being electrons and positives being the positive ions in association with an electron being absent from an atom, but it's a little more intricate than that. So the idea of an electron flow just being the opposite direction of hole flow or positive charge flow. You know, positive charges go in the opposite direction of electron flow. It's a good approximation, but it's not quite true. And a deeper analysis of that involves quantum mechanical considerations of the nature of the material and the state of the valence shells of the electrons. So that was a mouthful. And I'm going to kind of ignore that now. But this is important for the study of semiconductor materials that are in your computers. But let's get to the basic idea here. So we have a positive charge. And let's say it's moving with a drift velocity to the right. And there will be a upward force. Put your fingers in the direction of the B field, thumb to the right, palm points up. So the drift velocity of the charges moving through this magnetic field causes the charges to be pushed upward. And as a result of this, we have a charge separation. We have positive up on the top because of this magnetic field pushing them up, negatives on the bottom. But there's something else that happens here. When you have that charge separation and positive charges coming through here, they're going to be repelled by the positives up here and drawn toward the negative because of this basically induced charge separation. Well, we produce an E field because of this charge separation. That E field results in a Hall voltage, a voltage that's not an Ohm's law scenario. It's not because of current flow across here, but because of this charge separation, we get an E field and a resulting potential difference. Now, based on the size of that and the size of the current going through, and the nature of the magnetic field can be determined. The size of the magnetic field can be determined. Basically, if you continue to allow current to flow, we have this upward magnetic force, and that's QVB, and a downward QE force. And those will be in balance after a relatively short period of time. So as charge continues to flow through here, eventually it'll maintain that equilibrium situation. And you can actually measure the Hall voltage. Okay, so now considering these as negative carriers, we have our magnetic field. We have we'll just consider this an electron for simplicity, drifting the opposite way. Now you'll recognize with the right-hand rule that the magnetic force is in the same direction. So we end up, though, with negative charges on the top, positive on the bottom. So reverse that basic order. The electric field is directed like this, and once again we get a Hall voltage across here. The negative charge, the electric field, causes a force downward, QE force, and a QVB force upward, just like before. Now, drift velocity is E over B. This is kind of like a velocity selector, and the E over B consideration is the same as we discussed. Now, current density is number of charges per volume times the amount of charge times the drift velocity. Drift velocity being E over B, so we can rewrite that as NQ E over B and come up with an equation that equates the number of charges per volume to the current density, the magnetic field, the electric field. So this is all important in the study of semiconductor materials, for instance, being able to determine what this relationship is. Helps us understand materials better and the particular nuances of differences with different kind of semiconductor materials and adding impurities called doping it, and how that's going to work in your computer for making electronic devices, semiconductor materials, microprocessors, etc. And again, the size of the electric field can be determined by a sensor recording the Hall voltage and knowing what kind of magnetic field you would need with a given known material to produce this separation of charge, producing the Hall voltage, and sending a little current through, whether it's considered negatives to the left or positives to the right. All those things taken into consideration will enable you to build a little magnetic probe. So that, in brief, probably not brief enough, is the Hall effect. Just for practice, let's do a simple example of charges moving in a uniform magnetic field that's parallel to the x-axis. And let's just get the forces on each of these in each of these situations. So we have a B field moving to the right, positive x, and we have A, B, C, D, E. Those are each charges. And each one is going to be going in a particular direction. So let's start with A. A is moving in the positive y direction. So just get out your trusty right hand, stick your fingers in the direction of B, positive x, thumb points in this direction, the way the positive charge is moving. Does this say that? Well, we're assuming it's a positive charge. And so thumbs up in that way. Where does your palm point? Well, your palm points into the page, which would be negative z. So force on A, QV cross B, which is QVB. Things are perpendicular. Everything's perpendicular. And there's the direction of force. Now let's do B. All right, so again, fingers in direction of B, thumb in direction plus Z. Where does your palm point? We once again have a QVB force because the velocity is perpendicular to the magnetic field, and it's upward. How about C? C is moving negative x. Now, you try and do the cross product in that, and you run into trouble. Since the vector quantities are anti-parallel, you end up with no force. For D, let's move kind of kitty corner across here. Now, we have QV cross B, which is QVB sine of 45. So here's B. The V is cutting off at an angle with, if I could pretend I'm connecting this vector onto here, it's like this. So in this case, there is direction this way and direction this way. And so the size of the force has been diminished because they are not perpendicular to each other. And this, nevertheless, no matter how you cut this, with your thumb pointing this way or this way even-ish, okay, between the two, you still have your palm pointing down, just at a reduced level. And finally, let's do one in this direction. Okay, now we're a little bit tricky here perhaps. We have QV cross B as always. So fingers, thumb. Now your thumb is partly this way and partly this way. There's a part of the velocity is across this way, part is across this way. Now that makes a difference. If it was all in this direction, the velocity, the force would be into the page, negative z. If it was all in this direction, then it would be down, or negative y. So it's a combination of those two. Something like this. So a little bit spatially tricky, but hopefully that's sensible, and don't get tripped up by this. Ha ha. Let's do another basic example, and speaking of not getting tripped up, let's try not to. We have an 8 amp current vertically directed. So the V right now is vertical. So we have up and down. Wow. All right, here's our frame of reference, and that frame of reference, north, south, east, west, is like you sitting there, what it really is on the face of the earth. So north is away from you, south is in back of you, east is to the right, west to the left. So that's and then we have the up and down perpendicular to that. So make sure the reference frame makes sense. Then let's figure out the force on a 1 centimeter element with magnetic field in various directions. So when the magnetic field is east, which it is now, and then we're going to do south and then 30 degrees south of west. So east, we got F is equal to IL cross B. Everything is perpendicular. It's ILB. What direction is it? Fingers in the direction of the B field. Thumb in the direction of the current. Well, that goes into the screen. But into the screen is north, isn't it? So 0.54 newtons in. There it is. Now, how about south? So we're going to direct the magnetic field south. It means it's coming out of the screen. All right, fingers in that direction with thumb in the direction of current. It's really quite simple how that comes out. Which way did your palm point? Hopefully east. So F is IL cross B. The direction of the current and the B field are perpendicular. And the length we're talking about then is just that 1 centimeter. So ILB sine of 90 degrees, 0.54 newtons to the east. And finally, 30 degrees south of west. Now, my drawing isn't real helpful, perhaps. It makes it look like it's angling down. But 30 degrees south of west. Okay, west is to the left. But south, 30 degrees south, I don't mean to have this bent down 30 degrees. Because south is outward. So how do you really show that? I guess I'd have to have these straight horizontal and then, but this side over here closer to you than the other side. So it was my attempt. So just keep in mind that the magnetic field is not angling downward, but it's angling inward toward you or to the south. So now think of putting your fingers in that direction of the magnetic field, thumb up, and imagine the direction of your palm. Hopefully your palm is coming out of the screen, mostly straight out, but then angled off to your left a little bit. Does that make sense? So force is IL cross B. But because what we just did, we still have the magnetic field and current perpendicular to each other. So it's still 0.54 newtons. But now it's 30 degrees east of south. So south would be directly behind you, but then angled off to your left, as I said. So there is another basic example of forces on currents. Let's get a little bit of practice with torques on current loops, the magnetic dipole moment, and I should say just say magnetic moment, and energy in this configuration. So we have a B field, a current circulating counterclockwise. So if you grab your grubby right hand and wrap your fingers around this coil in that direction of current, your thumb points in the direction of the magnetic moment. Magnetic moment then is out. The size of the magnetic moment it's the IA thing multiplied by the number of turns. The torque is magnetic moment cross B. So it's mu cross B, NIAB sine of 90. Well, we have if you think of the mu coming out, cross it into the magnetic field. So you're swinging this outward vector into this vector, and your thumb points to the left. So that's NIAB negative I. It's in the negative x direction in this case. There it is, folks, direction of the torque. Now the energy, U sub B, is minus mu dot B. All right, you can go back and review that whole discussion if you so choose. Otherwise, just embrace it. Minus mu cross B is 0. There's no dot product because they're perpendicular to each other. Yay! In other words, this equates to a zero energy configuration. Doesn't mean it. Obviously, potential energy is always with respect to something. All right, so let's differentiate that from the next scenario. We have the current circulating the other way, the magnetic field going into the screen. So there's the magnetic dipole moment using your right hand, thumb pointing into the page. Now, torque is mu cross B. Oh, but wait a minute. Mu goes in, B goes in, both in the same direction, no cross product, zero torque. Energy, minus mu B cosine of 0. Well, if you remember that the dipole moment, the direction that it points, which is in, the torque is such as to try and line the dipole moment up with the magnetic field, which it's already done, which is another way to think of why there's no torque. So this is the lowest energy configuration, lowest amount of potential energy, which is minus mu B, which is minus NIAB. Okay, a couple more configurations. Let's this time have the current circulating clockwise, magnetic field straight up. Well, dipole moment into the page, right hand rule. Torque, mu cross B. Is there a non-zero torque? Let's see, this goes in, that goes up. Yeah, cross product is there. NIAB sine of 90, maximum value. See, what direction is it? Well, cross this vector going in into the B field with your right hand rule, cross product rule. Thumb should point this way. There it is. And the energy, minus mu dot B. Let's see. Yes. Well, no, there's no dot product, is there? They're perpendicular to each other. Zero, by definition. And one more. This time, we'll have current going counterclockwise. We have the B field going in. So mu is out of the page, and they're basically, the mu and the B field are anti-parallel, so no torque. But now the dipole moment and the magnetic field are anti-aligned. Remember, the torque always acts to align them, so the energy is in a maximal configuration because it wants to rotate, this dipole moment wants to rotate all around 180 degrees to line up with the magnetic field. So minus mu B cosine of 180, angle between mu and B, gives you mu B, the maximum value for the potential energy in this configuration. Or in any configuration, it's the maximum possible for this scenario. NIAB.